This video is going to go over Chapter 19, Objective 11, mechanisms that control homeostasis as it relates to the heart. So the pumping efficiency of the heart plays an important role in maintaining homeostasis. Blood pressure in the systemic vessels must be high enough to allow nutrient and waste product exchange across the walls of the capillary. So you've got to have enough pressure in order to move things out of the capillary into the tissues and back from the tissues back into the capillary. If your blood pressure is not high enough, that's not going to happen. So in order to meet metabolic demands, you've got to have a high enough blood pressure, which means the heart has to push blood hard enough out of the heart, the contractile force of those ventricles. The heart's activity must be regulated because the metabolic activities of the tissues change under conditions of exercise and rest. The body demands more when it's exercising, so the heart has to work harder to meet those demands of the tissues of the body. The two heart-related mechanisms that are involved in maintaining homeostasis are the baroreceptor reflex, which is involved in regulating blood pressure, and the chemoreceptor reflex, which is involved in regulating heart activity. Now, I'm going to tell you all up front, this is not the last time we're going to hear about the baro and chemoreceptor reflex. We are going to talk about those again in the next chapter, so those are going to come back and visit us later. You should have handouts in your packet for baroreceptor and chemoreceptor reflex. Let's take a look at the baroreceptor reflex. So the baroreceptor reflex is involved in blood pressure. So if we take a look right here, the baroreceptor reflex is detecting changes in the arterial blood pressure. Right here, it's picking up the pressure in the aorta. It is sending that information, take a look at that arrow, all the way up by way of the glossopharyngeal nerve to the, guess what, medulla, which is the cardioregulatory center of the brainstem. It's got a cardio-inhibitory and a cardio-acceleratory component, right? And then the medulla oblongata is going to make a decision on, okay, what is this information coming in telling me? So it's going to decide, do we need to speed up or do we need to slow down? If it is needing to slow down, it will send information by way of the vagus nerve, and it will target the SA node and tell the SA node to slow down, for example. I encourage you guys to take a look. You just need to watch about the first minute and a half of this video. So I encourage y'all to watch that video to help explain the baroreceptor reflex. I encourage you to watch this video to help explain visually what's going on with that baroreceptor reflex. So I'm going to go over it, but then you might want to go back and take a look at those videos to give you a better visual of what's going on. This animation right here, I'm just going to try it. I honestly don't know if it works anymore. Sometimes those McGraw-Hill animations are no longer active. I just wanted to try this first. Okay, that is no longer available. I wanted to make sure before I'm going to have to delete that animation, so this animation isn't going to work anymore. Okay, but you do have the other two, so thank goodness for that. So what you're seeing here, the baroreceptors detect changes in blood pressure. So baro means pressure, so it's detecting changes in blood pressure, which lead to changes in the heart rate and force of contraction. So based on the blood pressure, the heart is then going to act accordingly. Baroreceptors are a type of stretch receptor. So again, the more pressure inside that heart is going to then cause the walls of that blood vessel to stretch more. So pressure receptors, stretch receptors, that are going to be in the walls of large arteries, such as the internal carotid artery, which is this green little one right here. That is the internal carotid artery, and that's where one baroreceptor reflex is. Here's the other one, and the aorta. So right here is another baroreceptor mechanism that's picking up the stretch of the aorta and of the internal carotids. So right here is that carotid artery and that baroreceptor right there, and it's picking up the stretch. So again, the more pressure in that blood vessel, that stretch receptor is going to be activated. So this is just short-term regulation for changes in blood pressure. This is not a long-term effect. I know this is a busy slide. You've got this handout. So incoming information. Remember, afferent neurons are carrying information towards the central nervous system. So you need to know the definition of afferent, and that helps you understand what's going on here. So let's take a look at the blue. This is the carotid artery right here, and this is the aortic arch, and this is where your baroreceptors are. Those baroreceptors are going to travel to the cardioregulatory center of the medulla oblongata. So they're all targeting this area right here of the medulla oblongata. They're coming in by way of cranial nerve number 9 and cranial nerve number 10. Cranial nerve number 9 is the glossopharyngeal nerve, and cranial nerve number 10 is the vagus nerve. So these sensory signals are coming in by way of cranial nerve number 9 and 10. They're going to target and land at that cardioregulatory center in the medulla oblongata, and then that cardioregulatory center is going to make a decision about what to do with this incoming information. Now that we have the signal at the cardioregulatory center in the medulla oblongata, it is going to be interpreted and a decision is going to be made. So, based on what information comes in, the efferent action potentials are then going to travel from the medulla to the heart. This should sound an awful lot like homeostasis that we did back in chapter 1. So you've got efferent information, outgoing information traveling by way of the vagus nerve. Yes, that vagus nerve can have both incoming and outgoing information. We talked about that. It can also travel by way of sympathetic nervous system. Okay? Fight or flight response. So both the sympathetic and parasympathetic divisions, which would be the vagus nerve, to the autonomic nervous system, to the cardiac muscle cells. So sympathetic and efferent information is coming right here to this right atrium of the heart, the sinoatrial node of the heart. Okay, that is what is going to tell the heart to speed up. Cardioregulatory center. So right here is your cardioregulatory center of the medulla oblongata. Now the cardioregulatory center has both a cardioacceleratory component and a cardioinhibitory component. The cardioinhibitory component obviously is going to inhibit the heart from speeding up, meaning that's going to be parasympathetic stimulation. The cardioacceleratory component is going to be trying to speed things up, right? Fight or flight response. So if you follow the red lines, that's going to be the cardioinhibitory center. Let me make sure I'm reading that right. Parasympathetic. Parasympathetic is the blue line. The sympathetic is going to be the red line. So the blue line is going to be the cardioinhibitory response, and the red line, because it's sympathetic, is going to be the cardioacceleratory response. They're both targeting the sinoatrial node and the atrioventricular node. That's what the SAN and the AVN are standing for, letting the heart know if it's supposed to speed up or slow down. That information was sent in by way of the carotid artery and the aorta. Notice the green arrows right here going in to the cardioregulatory center where processing was made. So this is just an overview of everything. What happens if, and this is again one of those things where it's best not to memorize, it's best to understand what we're talking about, so that way no matter what question I give you, you can logically follow your way to the right answer rather than just memorizing, because there's no way you're going to be able to memorize all the different scenarios that I could give you related to a question over baroreceptors, chemoreceptors also. So if your blood pressure, for example, is elevated, how is that going to look? Well, the stimulus is the elevated blood pressure. Remember, the stimulus is what's wrong, what's going on. And that elevated blood pressure is going to be detected by baroreceptors in the aortic arch and the carotid body, the carotid arteries, because the increased pressure is going to cause those blood vessel walls to stretch. This information is going to travel from the carotid sinus and or the aortic arch to the cardioregulatory center located in the medulla oblongata by way of those afferent neurons that are going towards the medulla oblongata, located in the glossopharyngeal and vagus nerve. Remember, those sensory neurons are going to be traveling through cranial nerve 9, glossopharyngeal, and 10, vagus nerve. The increased blood pressure stimulus stimulates the cardioinhibitory center. So The increased blood pressure is going to tell the cardioinhibitory center, hey, you need to become active and you need to start telling this heart to slow down. So I need you to engage and slow the heart down. So the increased blood pressure wouldn't tell the cardioacceleratory center to speed up, right? It's going to target the inhibitory center, telling it to slow down. And it's going to prevent the cardioacceleratory center from continuing with the acceleration. So it's going to stimulate one and inhibit the other. The cardioregulatory center interprets the information and sends out signals by way of the efferent neurons that travel by way of the vagus nerve to the heart, and that's going to be the parasympathetic pathway, and the postganglionic neurons to the heart, that's going to be the sympathetic pathway. So the result is decreased sympathetic stimulation. We already have a high blood pressure. We don't need to make it higher, so we need to tell the sympathetic stimulation to back off, resulting in decreased heart rate and decreased blood pressure, and simultaneously telling the parasympathetic pathway to be engaged, and you need to start actively slowing and decreasing that heart rate and blood pressure. So I'm going to let you take a look at the decreased blood pressure example on your own, but that's just the opposite. So looking at the baroreceptors, elevated blood pressure within the artery causes their walls to stretch. So this is the arterial pressure right here. It's going to be between 70 and 110 millimeters of mercury. Now that increased pressure is going to cause a stretch to occur. That's going to cause those baroreceptors to pick up on that, meaning we're going to increase action potentials, and those increased action potentials are then going to target, they're going to be hitting the cardioregulatory center of the medulla oblongata. If you have low stretch, it's going to decrease the frequency of action potentials to the cardioregulatory center, and that's going to ultimately tell the cardioregulatory center, hey, you need to speed up. Send a signal to the heart telling the heart to speed up. So again, the elevated blood pressure triggers the baroreceptors to send a signal to the medulla. When blood pressure rises even more, the artery walls are stretched even farther, and the action potentials increase. Elevated blood pressure will result in baroreceptors reducing the sympathetic stimulation and increasing parasympathetic stimulation to cause the heart rate to slow down. This is just a summary. You can start right here with number 1, what if the blood pressure was high, and you can follow it around. Okay, take a look right here. The result is decreased sympathetic stimulation, which is going to result in decreased heart rate, which is going to result in decreased contractility, meaning the ventricles aren't going to contract very forcefully, and decreased cardiac output. That is then going to put you back to homeostasis. And then you can also follow it the other way. What if blood pressure was too low? How is that going to look? And again, you can see 4A right here. We're not going to talk yet about the vasomotor control, 4B. That's going to actually be in the next chapter. So when I said we're going to look at this baroreceptors, this baroreceptor reflex in both 19 and 20, we're going to look at this same identical page in chapter 20 where we're talking about blood vessels, and that's where we'll include this 4B component. So let's look at the chemoreceptor reflex. I told y'all previously several times that you need to know the relationship between oxygen, carbon dioxide, and pH, and this is where this comes in handy. So the chemoreceptor reflex is going to detect changes in pH and carbon dioxide. Believe it or not, you would think that your body is going to pick up information about the oxygen levels of the blood, when in reality it doesn't. It really picks up changes in pH and carbon dioxide levels. Oxygen is just, well, if you know carbon dioxide's high, oxygen's going to be low, and vice versa. But it doesn't really pick up the actual oxygen levels as much. So if you've got decreased oxygen and decreased pH, remember these two are the same. They're going to do the same thing. And then carbon dioxide is going to do the opposite. So if you have low oxygen, low pH, which means it's acidic, and high carbon dioxide levels, that is going to stimulate the vasomotor center, which will result in increased heart rate, increased carbon dioxide, and vasoconstriction. We'll talk about that in chapter 20. Ultimately, that will result in an increase in blood pressure, speeding return of blood to the heart. If you've got too much carbon dioxide in the blood, you're going to want your heart to speed up to try to get those lungs that are doing that oxygen exchange. We want that oxygenated blood in the heart going out to the rest of the body. So high levels of carbon dioxide in the blood is not good, so we've got to offload that quickly. So you want your blood pressure and your heart rate to speed up. Like I've said before, you need to know the relationship between carbon dioxide, oxygen, and pH. Good little chemoreceptor reflex video. You're going to watch from about 132 to 245 on this one. A really good little video, so I encourage you guys to take a look and watch that. So, the McGraw-Hill animation, I'm just going to go ahead and tell y'all this animation is not going to work, so don't even bother clicking it. Chemoreceptors, again, are really picking up pH and carbon dioxide levels. It helps regulate the heart activity. It is sensitive to changes in pH and carbon dioxide in the cardioregulatory center of the medulla oblongata. So, information about pH and carbon dioxide is going to where? Guess what? The cardioregulatory center of the medulla oblongata. It's still going to the same place. So a drop in pH, and that will also mean a rise in carbon dioxide. If one does one thing, the other's going to do the other. The cardioinhibitory centers are inhibited, causing a decrease in parasympathetic stimulation, resulting in increased heart rate. You got too much carbon dioxide. You've got to increase heart rate to get that oxygen going around the body, because remember that gas exchange is happening in the lungs. Cardioacceleratory centers are stimulated, causing an increase in sympathetic stimulation, resulting in increased heart rate and force of contraction. The increase in heart rate results in increased cardiac output, causing greater blood flow through the lungs, where carbon dioxide can then be eliminated. This helps lower the blood carbon dioxide levels back to normal, and then this stops. So again, this is going to be short-term type regulation. So again, chemoreceptors do not really directly respond to changes in oxygen levels. I know this looks like the same picture we had for baroreceptors, but look close, it's not. So number one, what's happening right here? So we're looking right here. You have got chemoreceptors in the carotid and aortic bodies. I know, same place that we had the baroreceptors, and they're monitoring oxygen, carbon dioxide, and pH. Honestly, more carbon dioxide and pH, right? And that information is going to pass by way of the vagus nerve, cranial nerve number 10, and cranial nerve number 9, the glossopharyngeal nerve, to the cardioregulatory center. The chemoreceptors in the medulla oblongata are going to pick up that information that is brought in. The decreased blood oxygen, increased carbon dioxide, and decreased pH decrease parasympathetic stimulation of the heart, which will then ultimately cause an increase in heart rate. So that information is going to be sent out by way of the vagus nerve, and it's going to tell the heart, it's going to block this signal right here and say, hey, we really don't want you slowing down the heart, we need you to stop. But we're going to really talk to the sympathetic nervous system. We want the sympathetic nervous system engaged. That's what we want to have happen if your carbon dioxide levels are too high. Decreased blood oxygen, increased carbon dioxide, and decreased pH, increased sympathetic stimulation. So again, look at these black arrows. We're gonna increase that sympathetic system to tell the sinoatrial node to increase heart rate and force of contraction. The decreased blood oxygen, increased carbon dioxide, and decreased pH, increased sympathetic stimulation, which also does affect these blood vessels right here, which is increasing vasoconstriction, but we will talk about that more in chapter 20. So chemoreceptors are sensitive to pH and CO2 levels found in the carotid and aortic bodies. Afferent neurons, remember that's taking information to the brain, to the central nervous system. Afferent neurons are going to bring information by way of the glossopharyngeal nerve. I spelled that wrong, P-H-A-R-Y-N-G-E-A-L, sorry about that. And vagus nerve to the cardioregulatory center of the medulla oblongata. Now, the cardioacceleratory center of the cardioregulatory center is going to send out signals by way of those sympathetic efferent neurons. And then the cardioinhibitory center is going to send out information by way of the vagus nerve. So the response of the cardioregulatory center is going to depend on what's coming in. and it's going to send information out by way of the vagus nerve. If it's trying to slow the heart down, it's going to tell the heart to slow down. Or if it's trying to tell the heart to speed up, it will send information by way of the sympathetic neurons in the sympathetic division. So efferent neurons, sympathetic and parasympathetic neurons arrive at the, guess what, sinoatrial node, that right atrium of the heart. So this is just showing you the pathway for the chemoreceptors. I've given you a place to start because, as you can see, it really didn't have a place to start. You have this handout in your packet there. So something's going on with homeostasis. In this instance, we have a decrease in oxygen, which means we're going to have elevated carbon dioxide. So the chemoreceptors are stimulated. Specifically, the cardioacceleratory center is stimulated and the cardioinhibitory center is inhibited. That is going to ultimately increase cardiac output and blood pressure, which is going to increase oxygen levels and decrease carbon dioxide levels and bring you back to homeostasis. Now, when we get to chapter 22, I believe, 21 or 22, when we talk about the respiratory system, chemoreceptors are going to come back in, and that's also going to affect the lungs. When we talk about the vasomotor center in the next chapter over blood vessels, we're going to see how those chemoreceptors are also affecting the dilation and constriction of the blood vessels. So again, the baroreceptor reflex mechanism and the chemoreceptor reflex mechanism are not going anywhere. So what is the effect of extracellular ion concentration on the heart? Extracellular means this is outside the cells, right? This is in the interstitial space. Well, here we go. So we've got our blood vessel right here, plasma, intervascular fluid. We have our cell. So this is the interstitial fluid right here. So when we're talking about extracellular, we're talking about anything outside of the cell. This is intracellular. This is outside the cell, whether it be in the plasma or in the interstitial fluid. So you need to know, we're only going to talk about a few ions here. So sodium rarely is going to cause enough change to deviate cardiac muscle function. Potassium, however, excess potassium, too much potassium in that extracellular space will cause heart rate and stroke volume to decrease. It's going to cause the heart to slow down. If you increase the potassium levels too much, it can result in heart block, which means a loss of action potential conduction through the heart. Keep in mind, too much potassium hyperpolarizes, which means you're going to have a super strong stimulus coming in to overcome that. And if you have way too much potassium, that's going to get it to where it doesn't matter how big the stimulus is, it's not going to cause an action potential in the heart. Reduction in extracellular potassium causes the resting membrane potential to hyperpolarize. Therefore, it takes longer for the membrane to reach threshold, resulting in a decreased heart rate. Now, calcium ions. Back in chapter 6, we talked about calcium ions and how it affected cardiac muscle cells. So an increase in calcium causes a greater force of contraction. Remember, the presence of calcium causes muscles to contract. Well, if you got a lot of calcium, it's going to really cause them to contract due to higher amounts of calcium. Increased calcium also indirectly affects the heart rate by reducing the frequency of action potentials created, reducing sympathetic and parasympathetic stimulation. Decreased calcium, however, increases heart rate. Now, how does the effect of body temperature affect the heart? Well, increased temperature causes heart rate to increase. If you guys have ever been outside, I know we just kind of came off of summer here. If you're outside, just sitting outside and it's 100 degrees outside, your heart rate's going to be going faster. Body temperature is an independent determinant of heart rate, causing an increase of approximately 10 beats per minute per degree Celsius, not Fahrenheit. I know we're used to Fahrenheit over here. The result is a dramatic increase of stress on your heart. So you can see right here the number of beats at 0 degrees Celsius. You have 0 beats at 0 degrees Celsius. And as the temperature increases, the heart rate is also increasing. So there's a direct relationship between increasing temperature and increasing the number of beats. So conversely, you would think a decrease in temperature causes the heart rate to decrease, Cold weather also puts an immense strain on the heart. Low temperature causes your heart vessels, your blood vessels, and your arteries to narrow, because remember, you're trying to conserve body heat, so your blood vessels are going to narrow, restricting blood flow and reducing oxygen. Your heart must pump harder to circulate the blood through those constricted blood vessels. So too cold or too hot, neither one of them is great. You want that nice homeostasis temperature. Okay, and then I'll let you take a look at those questions that are on your Moodle page over this chapter regarding set 11.